Hello, I'm Fable, and I'm here to narrate the secret to perfect surface smoothness, explained. The basic GD&T symbol for surface roughness. Surface roughness, or simply roughness, is the quality of a surface of not being smooth, and it is hence linked to human haptic perception of the surface texture. From a mathematical perspective, it is related to the spatial variability structure of surfaces, and inherently it is a multiscale property. It has different interpretations and definitions depending on the disciplines considered. In surface metrology, surface roughness is a component of surface finish, surface texture. It is quantified by the deviations in the direction of the normal vector of a real surface from its ideal form. If these deviations are large, the surface is rough. If they are small, the surface is smooth. Roughness is typically assumed to be the high-frequency, short-wavelength component of a measured surface. However, in practice it is often necessary to know both the amplitude and frequency to ensure that a surface is fit for a purpose. Now, let's delve into the role and effect of each technique. Roughness plays an important role in determining how a real object will interact with its environment. In tribology, rough surfaces usually wear more quickly and have higher friction coefficients than smooth surfaces. Roughness is often a good predictor of the performance of a mechanical component, since irregularities on the surface may form nucleation sites for cracks or corrosion. On the other hand, roughness may promote adhesion. Generally speaking, rather than scale-specific descriptors, cross-scale descriptors such as surface fractality provide more meaningful predictions of mechanical interactions at surfaces, including contact stiffness and static friction. Although a high roughness value is often undesirable, it can be difficult and expensive to control in manufacturing. For example, it is difficult and expensive to control surface roughness of fused deposition modeling (FDM) manufactured parts. Decreasing the roughness of a surface usually increases its manufacturing cost. This often results in a trade-off between the manufacturing cost of a component and its performance in application. Roughness can be measured by manual comparison against a surface roughness comparator, a sample of known surface roughness, but more generally, a surface profile measurement is made with a profilometer. These can be of the contact variety, typically a diamond stylus or optical, e.g., a white light interferometer or laser scanning confocal microscope. However, controlled roughness can often be desirable. For example, a gloss surface can be too shiny to the eye and too slippery to the finger. A touchpad is a good example, so a controlled roughness is required. This is a case where both amplitude and frequency are very important. Surface structure plays a key role in governing contact mechanics. That is to say, the mechanical behavior exhibited at an interface between two solid objects as they approach each other and transition from conditions of non-contact to full contact. In particular, normal contact stiffness is governed predominantly by asperity structures, roughness, surface slope and fractality, and material properties. In terms of engineering surfaces, roughness is considered to be detrimental to part performance. As a consequence, most manufacturing prints establish an upper limit on roughness, but not a lower limit. An exception is in cylinder bores, where oil is retained in the surface profile, and a minimum roughness is required. Surface structure is often closely related to the friction and wear properties of a surface. A surface with a higher fractal dimension, large Ra value, or a positive RSK will usually have somewhat higher friction and wear quickly. The peaks in the roughness profile are not always the points of contact. The form and waviness, i.e. both amplitude and frequency, must also be considered. Now, let's delve into the crucial parameters needed for achieving that perfect surface smoothness. A roughness value can either be calculated on a profile line or on a surface area. The profile roughness parameter, RARQ, are more common. The area roughness parameters, SARSQ, give more significant values. Now let's delve into the details of surface texture. The profile roughness parameters are included in BSN ISO 4287 20 British Standard, identical with the ISO 4287 1997 standard. The standard is based on the mean line system. There are many different roughness parameters in use, but RA is by far the most common, though this is often for historical reasons and not for particular merit, as the early roughness meters could only measure Ra. Other common parameters include RZ, RQ, and RSK. Some parameters are used only in certain industries or within certain countries. For example, the RK family of parameters is used mainly for cylinder bore linings, and the motif parameters are used primarily in the French automotive industry. The motif method provides a graphical evaluation of a surface profile without filtering waviness from roughness. A motif consists of the portion of a profile between two peaks, and the final combinations of these motifs eliminate insignificant peaks and retains significant ones. Please note that Ra is a dimensional unit that can be micrometer or microinch. Since these parameters reduce all of the information in a profile to a single number, great care must be taken in applying and interpreting them. Small changes in how the raw profile data is filtered, how the mean line is calculated, and the physics of the measurement can greatly affect the calculated parameter. With modern digital equipment, the scan can be evaluated to make sure there are no obvious glitches that skew the values. Because it may not be obvious to many users what each of the measurements really mean, a simulation tool allows a user to adjust key parameters, visualizing how surfaces which are obviously different to the human eye are differentiated by the measurements. For example, Ra fails to distinguish between two surfaces where one is composed of peaks on an otherwise smooth surface, and the other is composed of troughs of the same amplitude. Such tools can be found in app format. By convention, every 2D roughness parameter is a capital R followed by additional characters in the subscript. The subscript identifies the formula that was used, and the R means that the formula was applied to a 2D roughness profile. Different capital letters imply that the formula was applied to a different profile. For example, Ra is the arithmetic average of the roughness profile, PAR is the arithmetic average of the unfiltered raw profile, and SAR is the arithmetic average of the 3D roughness. Each of the formulas listed in the tables assumes that the roughness profile has been filtered from the raw profile data, and the mean line has been calculated. The roughness profile contains n ordered, equally spaced points along the trace, and yi is the vertical distance from the mean line to the ith data point. Height is assumed to be positive in the up direction, away from the bulk material. Let's dive into the details of how to achieve truly flawless surfaces. Amplitude parameters characterize the surface based on the vertical deviations of the roughness profile from the mean line. Many of them are closely related to the parameters found in statistics for characterizing population samples. For example, Ra is the arithmetic average value of filtered roughness profile, determined from deviations about the center line within the evaluation length, and RT is the range of the collected roughness data points. The arithmetic average roughness, Ra, is the most widely used one-dimensional roughness parameter. Parameter description formula, Rini average, or arithmetic average of profile height deviations from the mean line. $Ra equals frac1 LR int 0 LR left Z x right dx $RQ RMS quadratic mean, or root mean square average of profile height deviations from the mean line. $RQ equals SQRT frac1 LR int 0 LRZ x 2dx $RVI RV maximum valley depth below the mean line within a single sampling length. Average RV value over assessment length RVI equals min Z x $RV equals frac sum I equals 1 NRVIN $RPI RP maximum peak height above the mean line within a single sampling length. Average RP value over assessment length RPI equals max Z x $RP equals frac sum I equals 1 NRPIN $RZ I RZ maximum peak to valley height of the profile within a single sampling length. Average RZ value over assessment length RZ I equals RPI plus RVI. $RZ equals frac sum I equals 1 NRZIN $RSK skewness, or measure of asymmetry of the profile about the mean line. $RSK equals frac1 RQ3 left $RKU kurtosis, or measure of peakedness or tailedness of the profile about the mean line. $RKU equals frac1 RQ 4 left $RZ din, RTM average distance between the highest peak and lowest valley in each sampling length. ASME if 18.36 meters, 1996 surface texture symbols $RZ din equals frac1s, sum I equals 1 SRTI where S is the number of sampling lengths, and RTI is RT for the ITH sampling length. RZ GIS Japanese Industrial Standard for RZ, based on the 5 highest peaks and lowest valleys over the entire sampling length. $R text Z GIS equals frac15 sum I equals 1, 5 RPI RVI where RPI and RVI are the ITH highest peak and lowest valley respectively. Here is a common conversion table with roughness grade numbers. Roughness North roughness values Ra RMS muin, center line. CLA ISO grade numbers micrometers μ microinches muin, N12 52022 0 2011 25 1000 1000 100 1000 N10 12.5 500 500 and 5500 N9, 6.3200, and 5200 and 75-200, and 15.8 and 25-100, and 37.5-100, and 25 N7 1.6, 63 69.3, 63 N6 0.8 32 35.2 32 N5 0.4. 16 17.6 16 N4 0.28 8.88 N3 0.144.44 N2 0.05 22.22 none 0.025 11.11. Now let's delve into slope, spacing and counting parameters. Slope parameters describe characteristics of the slope of the roughness profile. Spacing and counting parameters describe how often the profile crosses certain thresholds. These parameters are often used to describe repetitive roughness profiles, such as those produced by turning on a lathe. Parameter description formula, RDQ. R delta the RMS of the slope of the profile within the sampling length $RDQ equal SQRT. Frac 1N, sum I equals 1, N delta I2, $RDA. R delta the average absolute slope of the profile within the sampling length $RDA equal frac 1N. Sum I equals 1, N delta I $delta I, where delta I is calculated according to ASME B46.1 and is a fifth-order Savitsky-Golay smoothing filter $delta I equals frac 160 dx. yi plus 3 9yi plus 2 plus 45yi plus 1 45y minus 1 plus 9y minus 2y minus 3 $. Other frequency parameters are S, M, lambda A and lambda Q. Sm is the mean spacing between peaks. Just as with real mountains, it is important to define a peak. For Sm, the surface must have dipped below the mean surface before rising again to a new peak. The average wavelength lambda A and the root mean square wavelength lambda Q are derived from delta A. When trying to understand a surface that depends on both amplitude and frequency, it is not obvious which pair of metrics optimally describes the balance, so a statistical analysis of pairs of measurements can be performed, e.g. Rz and lambda A or Ra and Sm, to find the strongest correlation. Now, let's delve into the crucial bearing ratio curve parameters. These parameters are based on the bearing ratio curve, also known as the Abbott-Firestone curve. This includes the RK family of parameters. Let's dive into how the intricate patterns of nature can unlock the key to flawless surfaces. The mathematician Benoit Mandelbrot has pointed out the connection between surface roughness and fractal dimension. The description provided by a fractal at the microroughness level may allow the control of the material properties and the type of the occurring chip formation. But fractals cannot provide a full-scale representation of a typical machine surface affected by tool feed marks. It ignores the geometry of the cutting edge. J. Paulo Davim, 2010, Op.Cit. Fractal descriptors of surfaces have an important role to play in correlating physical surface properties with surface structure. Across multiple fields, connecting physical, electrical, and mechanical behavior with conventional surface descriptors of roughness or slope has been challenging. By employing measures of surface fractality together with measures of roughness or surface shape, certain interfacial phenomena including contact mechanics, friction and electrical contact resistance can be better interpreted with respect to surface structure. ISO 25178, Geometric Product Specifications, GPS, Surface Texture, Aerial roughness parameters are defined in the ISO 25178 series. The resulting values are SAR, SQ, SZ. Many optical measurement instruments are able to measure the surface roughness over an area. Area measurements are also possible with contact measurement systems. Multiple, closely spaced 2D scans are taken of the target area. These are then digitally stitched together using relevant software, resulting in a 3D image, and accompanying aerial roughness parameters. Achieving truly perfect surface smoothness is surprisingly simple, as revealed in this comprehensive guide.